direct measurements for global temperatures only date back to the mid-1800s. So how do geologists figure out what past climates were like? Beyond the limits of direct measurements, we use proxies, which are preserved physical characteristics of past environments. And oxygen isotopes are the most commonly used proxy to reconstruct long records of past climate. There is oxygen-16, which accounts for the vast majority of oxygen, and there's oxygen-18, which accounts for most of the remainder. We don't care about oxygen-17 here. Water on Earth can therefore have H2O with either an oxygen-16 or an oxygen-18. Oxygen-16 is the lighter isotope with a lower bond energy, so in water it will preferentially evaporate over oxygen-18, which is the heavier isotope because it has a higher bond energy and will preferentially remain in water in the liquid form. This difference in mass and chemical properties leads to a process called isotope fractionation, meaning that the relative abundance of isotopes can change in a system. The degree of fractionation is temperature dependent, and cooler temperatures increase oxygen fractionation. So we can then apply this knowledge of how oxygen isotope fractionation works to understand past climates. The ocean has a set reservoir of oxygen-18 and oxygen-16. Water with oxygen-16 will preferentially evaporate, which then condenses into cloud vapor. When the clouds produce rain, water with heavy oxygen-18 will preferentially be rained out. As the heavier oxygen-18 is removed through precipitation, the resulting vapor and liquid will become lighter, meaning that there is a higher abundance of oxygen-16 to oxygen-18. Once the clouds reach the poles, the water will become locked in ice, which will thus be enriched in oxygen-16 and isotopically light. Conversely, the water in the oceans is now enriched in the heavy oxygen-18 because the lighter oxygen-16 has been preferentially removed and is now trapped in ice in the poles. But now imagine you don't have any ice sheets. Instead of oxygen-16 becoming locked in ice, it will cycle back to the oceans so that the oceans are no longer enriched in oxygen-18. Scientists can then take oxygen isotope measurements from either ice cores or deep sea sediments and measure the relative abundance of oxygen-16 to oxygen-18 and use that ratio to reconstruct past climate. If deep sea sediments are enriched in oxygen-18 and polar ice is enriched in oxygen-16, that indicates that the climate was colder. If you don't see that enrichment, that means climate was warmer because oxygen-16 wasn't being locked away in polar ice.